Randomness and probability. The general addition rule. The general addition rule is used to calculate the probability of the occurrence of at least one of two events. This rule is necessary when the events are not mutually exclusive, meaning they can occur simultaneously. For example, consider US banknotes. Most bills have pictures of famous buildings on the back. The $1 bill has the word one, and the $5 bill shows the Lincoln Memorial. We divide the bills into two events, A and B. A means odd denominations, $1, $5. B is odd numbered values, $5, $10, $20, $50, and $100. The $5 bills falls into both categories. To find the probability of selecting a bill that is either odd numbered or has a building on the reverse, we use the general addition rule. Conditionally probability and the general multiplication rule. Conditional probability. The probability of an event occurring given that another event has already occurred. It is written as 3 times A divided by B and calculate as here you can see general multiplication rule. This rule relates the probability of the intersection of two events to their individual probabilities and their conditional probability. It's given by A and B equals A times B divided by A. Here is a contingency table giving counts of the students by their goals and sex. Given the study 478 students, the probability of selecting girls is girl equals to 251 divided by 478 equals to 0.525. For more complex events, such as selecting a girl whose goal is to be popular, the probability is girl and popular equals 91 divided by 478 equals 0.190. The probability of selecting a student whose goal is to excel at sport is sports equals 90 divided by 478 equals 0.188. Independence. In probability theory, independence refers to the concept that the occurrence of one event does not affect the likelihood of another event happening. This fundamental idea is crucial in understanding how different events interact within a probability space. If two events are independent, knowing the outcome of one event pro- provides no information about the outcome of the other. Independent events. Independence means that the outcome of one event doesn't affect the probability of the other events. Mathematically, if events A and B are independent, A and B equals B times A divided by B. This means that the occurrence of one event does not change the probability of the other events. For example, girls have a 0.52 probability of getting good grades, the same as all students, indicating grades are independent of gender. However, boys have a 26.4% probability of being involved in sports, showing that sports involvement is not independent of gender. B divided by A equals B. Independent is not equal disjoint. Disjoint events cannot be independent because the occurrence of one event means the other cannot occur. For example, getting A or B in a course. These events are not independent because if one happens, the probability of the other occurring is zero. Depending on independence. Understanding and and evaluating independent events is crucial in decision-making process. However, assuming all events are independent can lead to incorrect conclusions. For example, in earthquake insurance, the probability of two buildings being destroyed in the same city is not independent. Therefore, when evaluating such events, the independence assumption should be used carefully. Featuring probability tables, Venn diagrams, and trees, tables, contingency tables, rows and columns represent different categories or events, and the cells show the coins or probability of their intersections. Useful summarizing and analyzing the relationship between categorical variables. Venn diagrams. Each circle represents an event, and the areas where circles overlap represent the intersection of events. Helpful for understanding how events overlap and the relationship between them. In the Facebook, Twitter example, 71% of online adults use Facebook, 18% use Twitter, and 15% use both. Their main ways to visualize these data area Venn diagrams, probabilities tables, and trees. The 0.71 and 0.18 are marginal probabilities in the table's margins. The 0.51 is a joint probability for using Facebook and Twitter, placed in the table's interior. Since the table's cells represent disjoint events, their probabilities add up to marginal totals across rows and columns, making it easy to fill the rest of the table. Tree diagrams. Diagrams that use branches to represent the sequence of events and their associated probabilities. Useful for mapping out multiple states of events and calculating combined probabilities for sequential events. We can diagram the three outcomes of drinking and indicate their respective probabilities with a simple tree diagram. Reversing the conditioning and Bayes rule. Understanding how to reverse conditional probabilities and apply Bayes rule is crucial for accurately interpreting data and making informed decisions. This topic delves into the methods of calculating the probability of one event give another, using real-world examples to illustrate the principles of conditional probability and Bayes theorem. Depending on independence. Understanding and evaluating independence events is crucial in decision-making process. However, assuming all events are independent can lead to incorrect conclusions. For example, in earthquake insurance, the probability of two buildings being destroyed in the same city is not independent. Therefore, when evaluating such events, the independence assumption should be used carefully. Reversing the conditioning and Bayes rule. Bayes theorem is a key concept in probability theory that updates events probabilities. This text explores using Bayes theorem and reversing conditioning. For instance, given given a student had an alcohol-related accident, what is the probability they are a binge drinker? Binge drinker. We need to reverse the conditioning from 3, which gives the probability of an accident given binge drinking. To find the probability of binge drinking given an accident, these probabilities differ and require reversing conditioning. Bayes' theorem calculates the conditional probability of events. Given a student had an alcohol-related accident, we can find the probability they are a binge drinker by reversing the conditioning. For instance, if the probability of an alcohol-related accident is 0.108 and the joint probability of binge drinker and accident is 0.075, then the probability of binge drinking given an accident is 0.694. Reversing conditioning, tough, not institutive, is essential for accurate probability conclusions. Bayes rule. Bayes rule allows us to find the reverse probability 3 times b divided by a when we know 3 times a divided by b. While we can use tree diagrams, Bayes' rule enables use to calculate it algebraically. Named after Reverend Thomas Bayes, this rule is fundamental in statistical analysis for two events. Bayes' rule is here you can see in the picture. This rule is essential for reversing probabilities and is the foundation of Bayesian statistics. This analysis demonstrated the importance of reversing conditioning to determine the likelihood of an event based on given probabilities. A recent Maryland highway safety study found that in 77% of all accidents, the driver was wearing a seatbelt. Accident reports indicated that 92% of those drivers escaped serious injury, like defined as hospitalization or death, but only 63% of the non-belt drivers were so fortunate. Question: what is the probability that a driver who was seriously injured wasn't wearing a seatbelt? Answer: let B equals the driver was wearing a seatbelt and NB equals no belt. Thank you for listening.